I think it's turned down. Can you guys hear me in the back? Thank you.
Okay, so our next speaker is Linda Yee from Caltech. Thank you for coming, and I hope your house is okay.
We're good.
And if you remember from Raphael's talk mentioning piezomagnetism, so I'm very interested to see what you have to say about this really nice introduction for Raphael about this subject.
Yes.
Thank you.
Thanks, Jackie, for the introduction. Yeah, so we had a really nice discussion already in the morning session, inspired by Leslie's talk about AI and material discovery. So here I want to really switch gears and really focus on this physical phenomenon called piezomagnetism. And the title of the talk is Piezomagnetism in Quantum Materials. And you know, the piezomagnetism itself as a physical property has been discussed from the perspective of symmetry for quite some time. And I hope through today's talk I can convince you that this is also a very good time to revisit this concept, and it's relevant to quite a few classes of emergent quantum materials, and hopefully can be a powerful tool to give us some new insight about those materials. I need to figure out how to proceed the slides. So this is sort of the outline of this talk. So first of all, I want to formally define what I mean by piezomagnetic effects. And in the second part, and discuss them, the effect from the perspective of symmetry. And in the second part, I want to be more concrete and give you a few cool examples that's recently studied in the field to show you examples of microscopic mechanisms of the piezomagnetic effect. And after that, I want to focus on showing you how to experimentally measure such piezomagnetic effects, and this part would be based very heavily on the kind of setups we have in our lab. Okay. So first of all, from the name piezomagnetism, right, you might have already guessed that it's sort of related to both the mechanical and magnetic properties of our material. So in order to put this to a broader context, I'm showing you this so-called modified Heckman diagram. So this diagram is intended to show the relations between the different thermodynamic variables coming from different properties of the material. So for instance, here we have three different groups, and within each of these circles, this pair of thermodynamic variables are so-called conjugate variables to each other. And for instance, for the electrical properties, you have the electric field and polarization, and for magnetic properties, we have magnetic field and magnetization. And for mechanical properties, we have stress and strain. So within each of those sectors, right, we can define susceptibility between susceptibility or elastic constant between within each of these circles. But perhaps what's more interesting is the cross correlation between the seemingly independent kind of properties of different materials. So broadly speaking, the cross talk between electrical and mechanical properties of materials can be categorized as the piezoelectricity, and the correlation between electrical and magnetic materials can be characterized by the magnetoelectricity, while between mechanical and magnetic properties, we have the piezomagnetism, which is going to be the focus of today's talk. Right. So this is a relatively complex diagram with a lot of a lot of lines connecting the different thermodynamic variables. So perhaps a different framework of thinking about those properties is instead to think about the relevant symmetries of each of those properties. So here I'm showing you a Venn diagram instead, where where each of these circles is representing the relevant symmetry for each of these branches of the physical properties. So, for instance, for the electrical properties, this is very intimately related to the inversion symmetry of a given system, and a global broken of the inversion symmetry would give one the ferroelectricity, right? And for the magnetic properties of materials, this is very closely related to time reversal symmetry, and the global broken of the time reversal symmetry is going to give us ferromagnetism. Right. So for the mechanical properties, and this part would be related to the rotation or mirror symmetries, and we'll see examples of those as we proceed. Great. So I do realize that the plot, this Venn diagram might be a little bit ambiguous in the sense that for the overlapping regions between the different symmetries, we should really think about them as the interplay between the different symmetries, rather than systems that has both the adjacent symmetries. Right. So as quite on the contrary, as we will see in our example of piezomagnetism, we will actually have to break a time reversal symmetry and sometimes the rotation mirror symmetries. So, anyways, the takeaway here is that piezomagnetism is a sort of a crosstalk between mechanical and magnetic properties of your material, and it's closely related to the time reversal symmetry and rotation and mirror and other crystalline symmetries of the system. Okay, so now I want to formally define what I mean by the piezomagnetic effect. So in the most narrow sense, the piezomagnetic coefficient can be, or the linear piezomagnetic effect can be defined as the sort of a susceptibility of the magnetization with respect to the stress or strain of the system. So here, within this talk, because for the experiment I'm going to show you, we're going to really control strain. So for convenience, I'm using strain here, but sometimes in literature you'll see stress here in the denominator. Right. So those two are very similar to each other, and they are only different from each other for an elastic moduli. Okay. So this piezomagnetic effect is a third-rank tensor, and in terms of its property under time reversal symmetry, it really inherits from the numerator, which is the magnetization. So therefore, the tensor itself is an actual and time reversal antecedent tensor. Right. So in other words, the piezo-magnetic effect would be forbidden if the system has the time reversal symmetry. And this again comes from the property of M under time reversal symmetry. And additionally, it will also be forbidden in systems that has the combined inversion and time reversal symmetry, which we denote as PT here. And also it's forbidden in systems that has a combined time reversal and translation symmetry. So in other words, for the in other words, the time reversal symmetry is a necessary condition for the piezo-magnetic effect, but it's not a sufficient condition. You actually have to break the time reversal symmetry you have to break it strong enough. So another important property of the piezo-magnetic effect from the property of the time reversal symmetry on magnetization is that in time reversal symmetry breaking systems, often we have domains that are connected with each other by time reversal symmetry, right? So the piezo-magnetic effect of those domains that are related to each other by time reversal symmetry would have opposite signs. And this is illustrated here where the linear relation between magnetization and the stress or strain applied to these domains would be of opposite signs to each other. So far I've discussed about a few conclusions we can get from the time reversal symmetry part of the piezo-magnetic property. So I want to pause here to just try to extend the piezo-magnetic effect to not only include the linear relation between magnetization and strain, but also include the inverse piezo-magnetic effect, where the strain or the lattice deformation would have a linear relation with the external magnetic field, and all these properties I've discussed is also applicable here. Right. So lastly, although the piezo-magnetic effect itself strictly speaking, is a thermodynamic quantity, but we can also try to extend the definition of the piezo-magnetic effect to include a few transport properties. For instance, we can extend this magnetization here as to the anomalous Hall effect, while for the lattice deformation here, it's an anisotropic deformation, we can extend it to resistivity anisotropy. Right. So care must be taken when we think about transport properties as the piezo-magnetic effect. That I wanted to include this here to include a wider class of phenomena that we can think about from the framework of the piezo-magnetism. So here, up to now, we've talked about the symmetry properties of the piezo-magnetic effect from time reversal symmetry. And in the next few minutes, I want to also talk about the symmetry effect, symmetry properties of this effect from the symmetry of the denominator, which is strain. So in this slide, I want to just throw out the definitions of strain in case you're not familiar with thinking about the lattice deformations. So in the most conventional sense, the strain there are two main categories of strain or lattice deformation, where the longitudinal strain involves the lattice deformation along the principal axis, right? And in the shear strains, the direction, in this deformation, the direction of the axis are also slightly deformed. So you can also think about the shear strain as a uniform deformation along the diagonal dimensions. Right. So that's the conventional categorization of the different modes of strains. But here I want to categorize the different modes of strains in the context of whether they break or preserve the original symmetry of the lattice. So here we have the example of a two-dimensional square lattice, and there for the in-plane strains, we can categorize them as those that preserves all the different symmetries of the square lattice, and those strains that would actually break the fourfold rotational symmetry and additional and also a few mirror symmetries of the system. So the actual forms, if you're not familiar with the actual forms of the strains here, it's okay. But the take home here is that we can think about we can categorize the strains in terms of those that preserves all the crystalline symmetries and those that would break certain crystal symmetries. So these two kinds of strains actually would have very different kinds of piezomagnetic effects. And for the symmetric strains, which does not break any symmetry of the original crystal system, it's the piezomagnetic effect. The relevant piezomagnetic effect would only take place if the system already has a net magnetic moment in its magnetic structure. Right. So here I'm showing you with a minimum set of spins to show you this piezomagnetic effect. So if we think about a pair of canted spins where it has a net moment in the x direction, right? So if we change the distance between this pair of spins, we do not change any crystalline symmetry of the system, but you can imagine the canted angle of the two spins can change, and therefore there can be a linear piezomagnetic effect between these symmetric strains and this magnetic moment that's sort of already there. So in some sense, in all ferromagnetic systems, this sort of symmetric strain induced piezomagnetic coupling is also allowed in the direction of the magnetic moment. So this kind of looks a bit trivial, and perhaps a more interesting kind of piezomagnetic effect would take place with the antisymmetric strains, which breaks the crystalline symmetries. So here I'm showing you an example of a triangle of three spins, which are 120 degrees from each other. Right, so this non-collinear spin structure here does not have a net moment, but if we apply a strain to break this threefold rotational symmetry, these three spins does not have to be 120 degrees from each other anymore, and therefore we can get a net magnetic moment in this case. So in some sense, you can view this new magnetization that wasn't there in the undistorted case to be a result of the broken rotation symmetry from the string, right? And you can also do the same thing for mirror symmetries, but I'm only showing you the rotation symmetries. So this is my symmetry discussion of the piezomagnetic effect. To summarize this part, all right, so you see that the piezomagnetic effect has to come with a broken time reversal symmetry. And additionally, there is a very intimate relation between the crystalline symmetry and the particular magnetic structure and the piezomagnetic effect. So very importantly, the piezomagnetic effect is not only applicable to ferromagnetic or systems that already has a net magnetic moment, but also applies to antiferromagnetic systems, which actually does not have a net moment. Right, does not have a net moment. So in other words, we may be able to use the piezomagnetic effect itself as a probe of broken time reversal symmetry, as I'll show you in a few examples. Okay. So great. So now let's move on to the second part of this talk, where I wanted to show you a few actual material systems that exhibit this piezomagnetic effect. So I'll start the discussion from the very first system that's discussed for its piezomagnetic properties, cobalt fluoride, and then I'll show you two pretty cool experiments I think from the field in recent years. So let's start with cobalt fluoride, which was the first material system that's discussed for the piezomagnetic effect. So it was theoretically discussed by Dilatometry in the 1950s, and it was experimentally verified very soon after that. So here on the left of the slide, you can see the crystal structure together with the magnetic order. Right? So here you have a tetragonal crystal, and there are two kinds of cobalt sites where, if you're at the corners of the squares, you have a spin up, while in the middle of this, for the body center of this region, you have a spin down, right? And also locally, for the cobalt atoms, there is the local crystal environment for the cobalt atoms has these fluorine atoms right next to them. So for the atoms at the corners, you have the fluorine atoms that's going to this diagonal direction, while for these body centers cobalt atom, you have the two fluorine atoms going to the other diagonal direction. Right. So as you might recall from yesterday's lecture by Raphael, that these two antiferromagnetic sites are related to each other by rotation symmetry, and therefore, symmetry-wise, it falls into it can be characterized by as an altermagnet. And it's a collinear antiferromagnet without any net moment. So from this magnetic structure, they allowed piezomagnetic coupling, would give us these three different off-diagonal terms, where you can see that YZ shear strain would induce X magnetic moment, and XZ to a Y moment, and XY to the Z moment, and so on. So experimentally, if we this piezomagnetic coupling was measured in a setup where you are able to measure the magnetization as a function of stress. And here you can see that without any stress, for the curves that labeled as 1, right? You see a linear MH curve that's characteristic as an antiferromagnet without any net moment. But this set of curves that's characterized by 2 is the MH curve after the application of stress. And you can see that there is a net moment that appears after the application of the stress. Right. Yes.
Can you do you know approximately what kind of stress is involved here? Is it
right.
percent?
Right, so I think we can go to this plot here. So here, this is the induced net moment as a function of the applied stress. So I think the unit here is in the unit of stress, but I think it would be on the order of 0.1%.
Yeah, I usually don't think about kilograms per.
Right, I actually can't. You can convert it to Pascal. Okay?
Yeah, thank you.
Okay, so you can see that there's a linear dependence of the induced moment as a function of stress, which fits very well with the definition of the linear piezomagnetic. So in terms of the microscopic origin of this, I think this original paper from JTP actually has a very nice illustration where here we have the top view of the magnetic structure from the z-axis. And you can see that if we artificially superimpose a shear stress in the xy plane, we will have this set of cobalt fluorine bonds that's longer than the other set of cobalt fluorine bonds, right? And this makes the two sides equivalent, and the magnetic moment of these two sides would be allowed to be different, and this would result in a z-axis net magnetic moment. Right. So, in any case, you can see that the key here is a strong interplay between the local crystalline environment as well as the orientation of the magnetic moment, and this, in principle, should also be applicable to a lot of the ultramagnetic materials that's discussed nowadays. Okay. So this is an example of the piezomagnetic effect in collinear antiferromagnets. And the next example I want to touch on is a non-collinear antiferromagnet, manganese-13, which together with its germanium cousin are two pretty well-studied systems in the past few years as antiferromagnets with a significant anomalous Hall effect. So the antiferromagnetic structure can more or less be seen in this middle plot of the undistorted states, where you can see this sort of forms this so-called triangular states on these for these manganese spins. And there's actually a net moment in the x direction in the particular phase, which is labeled as ms here. So as we have seen earlier in our very simple model, in our discussion of a very simple model of three spins, if we distort these triangles in the structural motif, we would expect the spins to start to rotate from each other, right? And since there's actually already a net moment, we would expect a linear piezomagnetic coupling between the lattice distortion and this magnetic moment, the net magnetic moment. And when this lattice distortion is strong enough, we might even expect to reverse the sign of the net magnetic moment. Right. And this is what And with this effect, this is what the Nakatsuki group was able to observe, where you see that as a function of the string, you're able to reverse the sign of the anomalous Hall as a function of the external magnetic field, and this really comes from this part of the piezomagnetic coupling. So, I wanted to show you this example to convince you that the piezomagnetic coupling in non-collinear spin structures might be a useful way to manipulate the antiferromagnetism to manipulate topological antiferromagnets. Okay, so the last example I want to show you here is perhaps the most exotic one, and this is the charge density wave state of the vanadium-based carbon metals, where there has been a lot of controversies of whether these states, whether the charge density wave breaks time reversal symmetry from muon and the Kerr effect. Right. So in in 2024, there are two different groups that have seen signatures of piezomagnetic coupling in these states, and I wanted to show you here just as a nice example of the piezomagnetic effect as a signature of time reversal symmetry breaking. So for this experiment I've showed you on the left of the slides, from the group of Philip Mall at Max Planck, you can see that this is a very carefully fabricated device where you're able to measure the resistivity along the three different directions in the hexagonal lattice, right? Without any broken symmetry, these three directions should be equivalent. But the surprising finding is that as you apply a z-axis magnetic field out of the cogomate planes, you're able to induce a significant anisotropy between the three different directions at low temperature. And this is equivalent this resistivity anisotropy is equivalent to the application of in-plane strain to the state. So in other words, this observation seems to suggest that there is a piezomagnetic coupling where the z-axis through which the z-axis magnetic field can induce in-plane distortion of the electronic states, and this is captured by the anisotropy in the resistivity. Right. So a very different experiment from the group of Vidya Mathavan at UIUC also suggests a very the same scenario where the signature there is a light-induced STM pattern changes. So as you might recall from the discussions that we have so far, the piezomagnetic coupling is only allowed in systems that breaks time reversal symmetry, and therefore it's highly likely the charge density wave states here actually breaks the time reversal symmetry. And to achieve this, one way is to form so-called loop current states on this lattice, and this is one of the possible loop current states that allows this piezomagnetic coupling. That's, I believe, actually proposed by Raphael, who's your lecturer yesterday. So I think since I've showed you quite a few different examples, I want to summarize here that we've seen that piezomagnetic coupling can be at play for collinear and non-collinear antiferromagnetic states, and possibly for the proposed loop current states, and they all as a signature of a broken time reversal. Okay, so in the remaining time, I would like to show you how to experimentally measure the piezomagnetism in more detail. And as I quickly mentioned, that this is very heavily based on the setups we have in our lab. And we can categorize those experiments in two main categories. So the first kind, we will try to measure strain. That's induced by the inverse piezomagnetic effect as a function of magnetic field, right? And in the second kind of experiments, we're going to try to control strain that's applied to the materials, and we'll be coupling this with either transport or thermodynamic probes, and hopefully I can convince you in the next 10 minutes or so that using all these those can all help us probe signatures of the piezomagnetic effect we talked about. So first of all, I want to focus on telling you how to experimentally measure strain. So this kind of measurement is called dilatometry, and to measure this length change of the crystal, roughly speaking, one can resort to microscopic measurements to high resolution X-ray or neutron scattering, or we can perform some sort of more macroscopic measurement, right? So one can do this through optical diffraction or through electrical measurements. And in our lab, we have a commercial capacitive dilatometer. And the idea of the experiment is really simple, where you have this your sample here that's shown as the blue block here. Right. And if there is metal plates that's movable together with the sample, we will be able to deduce the length change of the material from a capacitance measurements. Right. So the plot in the middle is to show you that you can also set up these capacitance measurements in a differential manner, which would really improve the resolution if there is a small displacement in between the two sets of jaws. So in the setup we have in our lab, the resolution is on the order of tens of picometers. And here is just a proof of principal measurements we've done with our dilatometer setup on a rare earth-based intermetallics, where you can see that it has a very sharp resolution of the different phases of the system. So with this setup, right, since we are able to measure length pretty precisely now, we can now apply this tool to study the piezomagnetic effect through the magnetostriction. So we've applied this on ultramagnetic candidate, chromium antimonite, where we got the crystals from Nini's group at UCLA. So this is the sketch of the magnetic structure of chromium antimonite, where you can see that those those are the two antiferromagnetic sites, and they are actually related to each other by the rotation symmetry. And it's called a G-wave ultramagnet because the spin polarization distribution in the K space sort of has this G-wave, it looks like a G-wave. So for this particular magnetic structure, there should be a few modes of piezomagnetic coupling within the AB plane, and those are the those are the expected coupled magnetic field and strain that's written out explicitly. Right. So we set out to do this experiment with the dilatometer setup, where we have the length change and the magnetic field along the y direction in this notation here. So you can see that we've seen a strong magnetostriction effect that has both a quadratic and a linear component, and the linear component is consistent with the piezomagnetic effect we've been talking about. So our next step is try to find a way to control the antiferromagnetic domains here, and hopefully we'll be able to show you that the piezomagnetic effect can reverse sign as we control these antiferromagnetic domains. So this is sort of one leg of the kind of measurements, and for the other the other experimental approach we take in our lab, we try to control the strain of the different materials. And we can, here are two typical strain setups we have in our lab. The first one is piezoelectric strain cell, where you can independently control the position of the two ends of this crystal that's mounted here. And then you can achieve a deformation of the crystals by the piezoelectric stacks underneath. And in the second setup, we have a 3-point bending device where you can use the screws to really bend the beam here. And if the material is long enough, you will be able to achieve a uniform strain at the center of the beam. So experimentally, after you deform the crystal using the strain setup, we will pair this with some sort of probe, and we can either pair this with transport probes, which measures either resistivity and anisotropy or anomalous Hall effects, or we can pair this with caloric measurement, where we have here in this particular setup, you can see that we have a little thermometer here that measures the temperature of the sample. Right? If we design this experiment properly, we'll be able to achieve a quasi-adiabatic condition, and this caloric measurement will allow us to measure the entropy of the system, and more precisely, the strain derivative of the entropy of the system. So I think for the remaining time, I'll just show you one single experiment where we actually use the latter caloric, the latter so-called elastocaloric effect to probe a quite elusive time reversal symmetry breaking order, the so-called magnetic octopole order. Right. So very quickly, let me just remind you of what magnetic octopoles would look like. So this is a series of progression from monopole to dipole and quadrupole to octopole. Right. So for inversion symmetric systems, the magnetic dipole would be the lowest allowed magnetic multipoles, and the next allowed magnetic multipole would be this magnetic octopole here. So the octopole breaks, if we have a static octopole order, it would break the time reversal symmetry, but the challenge here is that the time reversal, there's no net magnetic moment, therefore these octopole objects cannot very directly couple to the external magnetic field. So the piezomagnetic effect actually comes into the rescue here. So this octopolar angular distribution of the magnetic density actually allows piezomagnetic coupling, and here we can see that starting from the two-time reversal pair of the magnetic octopolar states, if we try to deform those objects in the XY plane, for instance, right, you can think about this deformation selectively enhance the magnetic intensities within the positive XY quadrant, and this would result in the object having a net magnetic dipole moment in the along the z direction, right? So in other words, through the piezomagnetic effect, through a composite string and magnetic field, we'll be able then to couple to the octopolar degrees of freedom. So the third column here is sort of illustrating the piezomagnetic coupling for the octopolar degrees of freedom in the reverse order, where you apply the magnetic field first, and this would induce deformation in the shear strength. So in principle, if the octopolar degrees of freedom couples to this composite field of string and magnetic field, we'll be able to probe them from the entropy perspective, and even at parallel quadrupolar states where these octopolar states where this moment does not order, we would expect to see a octopolar susceptibility response that's that has a specific field and strain dependence. So with this, we're actually able to see susceptibility-like response from our elastocaloric measurement, where this susceptibility is extracted by extracting the coefficient of the elastocaloric effect as a function of magnetic field and strength. And this is all, and this is one of the first thermodynamic probes of this really elusive time reversal symmetry breaking octopolar fluctuations thanks to the piezomagnetism of these elusive orders. Okay, so I think with this I want to just summarize where we've learned that the piezomagnetic effect is a crosstalk between mechanical and magnetic properties of a given material, and it has to come with a broken time reversal symmetry. And I've showed you a few examples that the piezomagnetic coupling can be a powerful tool to detect those elusive time reversal symmetry breaking orders. And for antiferromagnetic materials, they can be used to manipulate the antiferromagnetic order, and hopefully we are also able to apply this piezomagnetic effect to better manipulate the electronic properties of these emerging class of materials of automagnets. With this, I want to thank the funding agencies who are supporting our current research, as well as the members of my group. And for the octopole part I was talking to you at the very end of the talk, I want to thank my colleagues and collaborators at Stanford. So with this, I want to pause here and take questions from the audience.
Thanks, Linda. Okay, time for questions.
So you have it written that it's forbidden in systems with both translational and time reversal symmetries. If you had a system that breaks time reversal but has translation, is that still?
Right. So what I should clarify that what I mean here is a system that has a combined time reversal and translation symmetry. So if you think about a simple neo antiferromagnetic order, that would fall into this category. Yes.
So, I mean, told this non-collinear antiferromagnets, so there is no chance for the ferromagnetics to convert it piezomagnetics.
Right, so I think in some sense so the piezomagnetic coupling is allowed for ferromagnets. It is allowed, but I think the effect is more likely to be stronger in non-collinear antiferromagnets because naively, right, in ferromagnetic systems, the moments are already aligned, and even if you deform the lattice, the amount of changing the magnetization you're going to induce is not going to be that large. And in non-collinear antiferromagnets, I think the piezomagnetism-induced changes in the magnetic structure is likely to be stronger. So that's why I emphasize on the non-collinear antiferromagnetic part. But you're right. In ferromagnetic systems, a piezomagnetic coupling between the moment and string is allowed.
Bruce? So, going back to this slide up, this isn't the only possible orbital that would carry a multipolar moment, right? Mm-hmm. You have, they correspond to L equals 3 orbitals, so there'd be 7 of them.
That's right. So this is just a simplified picture. And
so is there any difference in the response to strain of the different orbitals that carry an multipolar moment?
That's a great question. So I think in general all the orbipolar moments all allow a piezomagnetic coupling. But in this particular TXYZ case, we allow a piezomagnetic coupling between the XY shear strength to a Z magnetic moment, for instance.
Right.
But for other types, it would be different. I think for the more planar type, I think it's an inclined string and inclined coupling.
I just want to comment on this, if that's okay.
Yeah, sure.
In the outer magnet, so in this specific video and in the low perovskite, you do have the atomic level, you have all moments from the non-ferrous elements. Mm-hmm. The outer magnet is a little trickier because you have a spin density that if you expand, the main contribution is actually less rate contribution, but it cancels at different sides. And then you have a residual contribution that is alcohol and so on. It's not like a local property like this. They have the same response in terms of outer magnets, but I think that the characterization is a little different.
Right, so
microscopic point of view, probably impact the size of the effect. But again, it's just speculation.
Right. I think maybe for outer magnets, it's better to speculate the coupling between strain and the transport properties, for instance, because they are itinerant. But I think it's symmetry-wise, these effects are allowed, and I think it will be interesting to study them in transport, for instance.
So I have a question.
Oh, yes.
Back to the Philip Mole experiment.
Oh, sure.
So you're suggesting this is a signature time reversal break, ultimately, right? But then why doesn't it onset at the charge order transition? Do you have a comment about that, or?
It seems to offset around 20 Kelvin.
Well, I think this is this ink set is sort of the temperature dependent of the anisotropy, right? So I guess, it's, if you have a magnifying glass, maybe it offsets around that temperature.
Yeah. So there is an anisotropy that onsets.
There is a tiny anisotropy.
Okay, fair enough.
Let me ask you a question. When I was looking at this data, there was a figure in the supplementary that claimed that this effect was actually even different, which I don't understand at all. I don't know if you have more insights about that or not. It's like very in the end of this implementation.
Right.
One, and I don't
Yeah,
understand.
that's not. Yeah, that's a bit.
Weird.
Right. That will be slightly different than the type of piezo-magnetic coupling we've been talking about. I wouldn't expect it to be even.
Any student comments or questions?
Maybe we should go to coffee break.
Okay, one more from Bruce.
So, again, while you have this up there, what is the evidence for time reversal symmetry breaking from STM in the you mentioned this?
Right. So I think I don't have the figures here, but to put it in words, I think the experimental observation was so they applied linearly polarized light to the material, and they've observed that you can swap the order of the intensity of the peaks of the charge density wave by this linearly polarized light, and this change of this order is similar to the effect of the z-axis magnetic field. And at the same time, they are also able to extract the lattice constant change. So I think the observation is the linearly polarized light-induced charge density pattern change, but it's proposed to come through the piezo-magnet, but by the light inducing a lattice deformation, and the lattice deformation through a piezo-magnetic coupling induce the charge density wave intensity change.
Okay, we have to move on, so thank you very much. Okay, picture time. So put your makeup on and button your shirt, and meet us in the bottom of the atrium.